nice to meet you all. A pleasure to have you here. I have this time to share my work and you to know Patagonia a little by photograph and by our work. So I hope you enjoy this, and I hope you wait for your questions. They will be very useful. So I will just put there who helped this work is Rita and Conicet, who paid my scholarship in Argentina, and here the University of Vermont, who helped me to come here. And this is our group. It's an agroecology group. If you want to scan the QR code, you can see what we do in Argentina with our topics and our working lines. This is what I'm going to tell to you today. First, I will introduce you to what is Northwest Patagonia, how is that climate, where is this place, then why we started working in soils, why this is important, and then how I went here, how I started working here, and then the work we made with some colleagues for soil organic carbon mapping, and then how we assessed the impacts of land uses. And at the end, some conclusion and projections for the future. And at the end, we have time for questions and discussion. Well, first of all, where is Patagonia? So here we are at the University of Vermont. If you zoom out and travel like in 1 second, we will be at the South America. So this big region, as you can see, is very dry in the most part of the eastern part. Is the steppe we call. We're going to see some pictures. And in the west part is the forest area. It has more precipitations. So you can know it is almost 41 latitude south. The winds come mostly from the west. And this is the place where I live now. It's called San Carlos de Bariloche. And here we have a chemogram where in the middle we have the winter, the July, we have the winter in bars from here. We have more precipitation in winter, in autumn also, and the summer is very dry. As you can see, we have low precipitations in summer, and the temperatures are very high. So as you can thinking, the climate change is a problem for us, because in this place, the temperatures are going high and the precipitations are going low. Nowadays, this is occurring. So why is this? The winds from Chile come from the sea, loaded with humidity. When they go up into a mountain, they drop most of the humidity in the mountains. And when the winds go to the east, they go almost dry. So the values of precipitation are almost 3,000 millimeters per year. And in the steppe, we only have less than 300 millimeters. So it's very dry and it's not suitable for agriculture, only for livestock production. And in the middle, we have different landscapes. So this is the steppe, as you can see. For example, what vegetation we have short shrubs, grasses, and many coverage of bare soil rock. For example, this is a common farm in the steppe. As you can see, you cannot go into the farm with motorcycle or vehicle because it's very steepy and it's very complicated to move. So the people move by horses. And this is a very common production in Patagonia. As you can see, the sheep production was historically very important, the fiber production of the sheep. And the dogs are really useful because the distances are very, very high. And also there's snow in winter, but as I told you, it's not so much precipitation. So these moments when snow occurs are very useful for the productions. And also in the western part, we have the Andes. We have many vegetation types. This is, for example, a photograph of summer. As you can see, we have forest in the hillsides of the mountains. We have shrubs in the middle, or maybe other forests. It depends on the place. You will see some maps of how many vegetation types we have there. This is a picture of the fall. As you can see, some of the trees are evergreen and others are fall their leaves. And in the upper part of the mountains is bare rock. It's different from here. Here we have forests everywhere. There is very high, and we have it's very cold also, so you have almost no vegetation. And this is a picture of the winter, so you have many things different in Patagonia. So as you can see here are the most commonly land coverage of this area. This is our study area. This belongs to Northwest Patagonia. And as you can see, in the western part, we have the forested areas. And in the eastern part, we have the steppe. And all the red zones are bare rock or no vegetation areas. And only the agriculture, I mean, the areas completely converted to agriculture represent only the 5% of this area, okay? But also in the steppe and in the forest, there are certain uses like livestock that are present. Here I will show you some pictures of what we are doing in Patagonia. For example, in the western part of the forested area, this is a very common livestock production in the forest, like sometimes grasses and sometimes forests. And this is also sheep production near the houses of the producers. We have also seasonal cultivation like horticulture, perennial cultivation like fruticulture. Tourism is very important in all this area, like the upper picture. But in the east, because we have less precipitations, the productions we have is sheep production and forestry. Because this is the climate doesn't allow to make these productions. We don't have so much rains. So we have this production in Patagonia, but the forecast, and we are already living this in everyday life, the temperatures are being higher, and the precipitations, the total are lower, but also when it rains, it's very concentrated. So this is a problem because the water that falls many times run off and the soil doesn't capture this rain. And also there are floodings and some problems because of this. So as you can imagine, this is not good for our productions. So we were thinking, what can we do in this situation? What as managements or land users, what can we do? Well, we started to think, we can think about our soils. These are all the functions that our soils give. For example, carbon sequestration, production of food, water purification, climate regulation. So in the context of climate change, maybe we can enhance some functions to face this problem we are having. Are you following me? Yeah? So there are some soil parameters like soil organic carbon that have a good consequence in the soil. If we increase the soil content, the soil organic carbon content in the soil, we have more productivity and more water retention capacity. Two things we need in this time of climate change. So this can be a good way of adaptation to climate change. Another thing is that also globally, agriculture, forestry, and other land uses account for 24% of global greenhouse emissions. So also, if we capture more carbon from the atmosphere, we are also helping to mitigate climate change. Okay. So the background of we want to increase our soil organic carbon of the soils, but how are our soils? They have carbon, how much they have? We actually don't have much information. What we have about our soils? We have soils mapped at very broad scale, so this is not useful to map or to understand how is our carbon in Patagonia. We have some maps, but for example, they are mapped for whole the country. They are not very precise for our place. So this can be useful, but if we want to understand, for example, certain type of forests, how they help to our soils, we don't know. And they are also mapped for 0 and 30 centimeters. And there are also some works of forested areas about soil organic carbon, but they are not also so precise. So because of this background, and because also in this region, we will know which is the impact of human use over the soils. We don't know what happened to the soils, regionally, after we make forestry or after we make cattle production in the forest. So other objective we have is to understand which are the impacts of human use over our soils. So this is our objectives, map soil organic carbon for all this region, but in the first 60 centimeters depth. Estimate carbon sequestration, but for different vegetation covers and different ecosystem types. Because of this, we need a very high resolution maps to make good summarize, because otherwise the estimations are not good. And finally, we want to assess which is finally the human impact for soil organic. So now I tell you how I get here, because this was our objective in Patagonia. And my objective was, okay, I had to make map soils, and I don't know how to make them. So I was searching in the website. I have a friend from here, it's Noelia Barrios. She contacted me with Gillian. Gillian and Moctava are very good at making map soils.
I'm over here.
How are you? And we said, okay, let's make a project. Maybe we can work together, and we can share. Maybe I can share my data, you can share your knowledge, and we can make a collaboration. So we write the project, and in November and December, and in April, I obtained this Macmillan scholarship. And before traveling, we started recompilating many data we need to make predictions. This is a thing we can do remotely. We had some meetings, and we started working, because when I arrived here in July, we have all the data to make the modeling and to be more efficient in our work. And in August, in only 2 months, we have very good results, and we have this first mapping of Patagonia and predictions like to make a manuscript, for example. Well, what I bring here, well, this is our study region. This is, you already seen this, but I want to show this, that Patagonia, this study area, not all Patagonia, is 4 times the size of Vermont. So it's a big area to go and take samples. It's very hard. We don't have so much resources, so each soil sample is very appreciated. So this was all the revision I made to find a total of 29 documents with soil data. And with this, I got less than 3,000 soil samples of different land coverage, present sites, cultivation, seasonal cultivation, perennial cultivation, livestock, and forestry. This is a detailed map of what land coverage we have. Here you can see that in the east we have mostly the steppe, but as you can see in the top, there are many different colors of different forest types. We have so many different forest types that are very interesting to understand how they work, and regarding soil organic carbon, if they are important or not important, or how much important they are. This is the soil database. In this map, it's shown the biozones, like for example, the Andes biozone, subandean grasslands, or the Central Plateau. They are different divided biozones. But the most important here is that the most commonly measured variables are pH, organic carbon, bulk density, and organic matter. So this is very useful because we need these 2 variables that I will tell you now how I use them. So this was the first work we did remotely. We compilated 43 variables from different types. For example, climate. Here you can see precipitation that is higher on the west. We have temperature, altitude. This is the slope. There are many, for example, many variables derived from altitude that we can use to predict. Maybe they are useful, maybe they are not. We put this into test. Middle probability, geology, the NDVI, I don't know if you heard about it. It's very common to study vegetation, and the blue one. But like this, we have 43. So after this, we stacked all these variables, compressed them into one file, and then we extracted all the environmental data for each soil sample to have, okay, we have all the samples, all the data, and also the environmental variables of each soil sample. So after that, we started to work with the data. This is a brief tale of how we work with our data. This first step is to select which variables are important for predicting. this is not important, just to know that we selected most of them maybe were useful for predicting. Then we ran 3 different predicting models. Maybe you heard them: random forest, QBIS, and gradient boosting. This is important because this model may let you select 80% of the data to train the model, and then you can leave 20% to validate it. So there's 20% that you supposedly not to know what is there. You predict with the model, and then you try how good is it. Okay. But here we have some problems. And here starts the processing issues. As you can imagine, you have a lot of data, and it is not easy to manage. For example, for random forest models, only for soil organic carbon from the first depth is 0 to 30, we have more than 6,000 models to test. So this is a lot of processing time. And this was a problem when we had to run all of this to our data. And also, what we had to do is, after we tested the 3 models, is to select which is the best. And with the best one, we had to predict for all over our region. So because it's too big, we divided in many parts and made predictions for each part separately. As you can imagine, we have a lot of prediction to make. More than 800 of rasters is a data set to be predicted. So that these violet things, I put it because I will tell you how we solve this. And finally, we need to estimate how is the final amount of carbon per hectare we have. And for this, we needed 2 variables. Soil organic carbon is the content of grams per kilogram of soil, but we also need to know how much soil we have in each pixel. So for that, we also need soil bulk density. And with the function multiplied by the depth and divided by 10, we get the value of tens per hectare. So as you can imagine, we have to predict also for soil bulk density and for 2 depths. So this work was multiplied by 4. So we had so much work to do, and my laptop was not good for this. So and also this step, we had to analyze at the same time more than 100 million pixels. So this was also another problem for our process. So what we did, we are very lucky because in the UVM we have the Vermont Advanced Computing Center. Don't know if you heard about it. I was able to log with my NetID. I had some meetings with the team. They helped me with like personal meetings and email feedback. And I have some issues in 2 things that I had 2 meetings more. But only with this, I was able to process all this data I showed you very, very quickly. For example, the processing times were maybe more, I can say, reduced by 90%. Also, for example, the RAM of my laptop was not enough, and in the back we have a lot of RAM we can use. And this is also very useful. I was able to send 4 jobs at the same time. Here I can show you, for example, this is a common screenshot you can see from the back. I was running soil organic carbon for 60, 30, soil bulk density for 60 and 30, and they were running for maybe more than 23 hours each job. And they have maybe 128 of RAM, so many processing cores, and even with that, it was so processing hard. But after 1 day and a half, it was finished. These are the results. Okay, what we found. The best model to predict, for example, soil organic carbon for the first 30 centimeters depth was 64% of confiability, of goodness of fit. We have this amount of samples, and for example, the soil bulk density, this one, it had much more precision. Here's the graphic, as you can see, predictions of the model versus observations. What we want is that all the points are aligned into this line, but sometimes the predictions are not perfect. But anyway, here we can see how good or bad are the predictions. So
those dots are the 20% that you held out?
No.
Is that everything?
It's not everything because it's more complex, because it's a scaffold system. In the scaffold system, I choose number 5, for example. and this divides the data in 5 parts. So in the first test, it trains with 4 and validates with that. In the second test, it validates with the other. It trains with the other 4 and validates with the other 1. So it is run 5 times. It's a different validation and testing process, but this is all the data. Yeah. Good question. Well, and this is very important also. So which variables finally were important for predicting soil organic carbon? In this graph, we have in the x-axis the variable importance. Here are all the variables for predicting the most important, and here is the sum of importance for predicting soil organic carbon. This is 0 to 30, and this is 30 to 60. As you can see, the most important variables were those derived from remote sensors and also derived from climate. Land coverage, derived from altitude appeared, but they were not so important as the other ones. And we did the same for soil bulk density. Also, the climate and the derived from remote sensors were the most important, and the altitude were important, but not so much. The list continues below, but these are the most important. So this is our final predictions of our region. This is the first depth of 0 to 30. As you can see, and as maybe you can imagine, in the west we have more soil organic carbon, and here are the values. Maybe they can arrive to 20 or more. And in the east we don't have so much soil organic carbon. We also estimated the interval of confidence. What is this? Is how much confidence we have, or which is the range we have much or very confidence of our data. We chosen an interval of confidence of 95%. I mean, we have 95% that our data is this value and between the values that are shown there. For example, if the value here is 18, it's 18 plus minus maybe is 0.7, for example. So it's 18, maybe 19, or maybe 17. But we have, it's very important when we make predictions, how much sure we are about this, or which is the error we are making. Because if we show this and we don't show that, don't trust those maps. Always look at the error. So this is the result for 0-30, and these are the results for 30-60. As you can see, it's lower everywhere because it's mostly concentrated in the upper part of the soil. We did the same with soil bulk density. Also, in the west, we have less soil bulk density. This is related with the functioning of the soils and all the productivity we have in the west. And for example, all the forests leave a lot of organic matter that falls, and this increases the soil porosity. So this is very related with the vegetation we have. And here is the other map of the 30-60 of soil bulk density. As you can see here, we have a little more error. Maybe we don't have much data there. A possible projection of our work is to take samples there and to improve our estimations in that part. So with the map, let me see the time. With this map, we then summarize how much carbon we have in each vegetation type. And this is a summary of all the pixels of all our study area. So the values are shown in tons per hectare, and all the green bars are forests, the orange are steppe or herbaceous, and the cyan are shrublands. As you can imagine also, the forests hold the most organic carbon per hectare, and the steppe is much lower, and it's related with the precipitations, okay? But there's something interesting I want to show you here, is that we also estimated how much carbon we have in the whole region. We want to sum how much carbon we have in total, okay? So first, this is the area. This is the area in square kilometers, and they are all our vegetation types. So as you can see, the steppe leads first with a lot of area of kilometers. So as expected also, regarding that the steppe didn't have so much carbon per hectare, it counts for the highest carbon sequestration in our region. Okay? And also this is the lenga, this is a very important vegetation type. It was the forest that lost their leaves that I showed you before. They are very fragile ecosystems, but they hold a lot of organic carbon, and it's very important to conserve them. And here, this is a good result because this shows that they are very important also for soil organic carbon. And because here they look similar, I added a log scale, so we can see if there are or not difference between them, and we can see that yes, there is some difference, but not so much as the steppe and this Pumilio, that is lenga, is the second most important in our region. So until now, we have estimated how much organic carbon we have in our region, but now other question we have is, which is the impact of human use over the soils? This is very important because this determines land uses, for example, or land management or land planning. So we assess this, or which is the effect of human use over soil organic carbon as the difference between current soil organic carbon, we have samples of that, minus the soil organic carbon content at, as it were, a pristine site. We have a lot of data from pristine sites. I won't show how we calculated this because it's long, but it's another model to estimate how the soil will be without human use. So these are the results. I want to explain a little. In the x-axis, we have the effect of human use. I mean, if the result is 0, it means that there's no difference between human use and pristine site. If it's positive, I mean in the right, it means that it has a positive effect of human use. And if it's in the left, it has a negative effect. As we can see, all of them are different and are different from 0, and also are different from them and are negative. The less negative maybe is forestry, showing maybe 2% of soil organic carbon loss, but perennial cultivation is the worst for soil organic carbon, and seasonal cultivation like horticulture also reduces soil organic carbon. And livestock, because maybe, as you can imagine, you do not remove the soil so much, only the cow maybe or the sheep are walking, they're not removing the soil. Maybe this helps to keep the soil organic carbon in the soil. And we also make some estimation of okay, in this vegetation type, what is the impact in general of the human use of each ecosystem? For example, in the meadows or in the steppe, we can see that there is not much difference from 0, and maybe there's not so much impact. But in these 3 forests, it's important. And particularly in this one is cypress, and another is no cypress. It looks like the soil is very fragile there, and we have to take this into account if you want to use these places. So, as a conclusion, we obtained the first high-resolution maps for soil organic carbon and bulk density until 60 centimeters depths at a very high resolution. We were able to estimate carbon sequestration for each land coverage by area unit and the total amount of stocks. And we found that in general, we are losing soil organic carbon as a consequence of human activity, so we had to think a little more about this. We found that the loss depends on the ecosystem type, and maybe with this we can promote or discourage activities in certain areas. And finally, our projection is, well, first of all, communicate what we found. For example, publishing or giving seminars like this, or maybe in other journals. How different Patagonian land coverage help to sequester carbon, and which is the impact of human use over the soil coverage. As you saw before, we have a lot of other parameters that are very interesting, maybe pH, maybe conductivity, that reflect how are the soils. So we also would like to assess what's happening in our region with that other data. And after we make this, we can maybe be able to estimate also regionally, like mapping, which are the soil functions that are very important. For example, which is the soil water retention capacity of our soils? We don't know. Well, with these parameters mapped, we might be able to do that. And also soil fertility, because we have nutrient data also. Before finishing, I want to thank you very much, the UEM and Lilian, because of them I was able to come here, and the GAN Institute for receiving me. Moktaba and Hannah are colleagues who we work very nice together. And thank you for hearing me all this time. And if you have any questions or comments, please let me know.